There's a cooling system you can build this weekend for under $300 using pipe from a hardware store in a trench in your backyard. And it works on the same physics that the U.S. Department of Energy has been documenting since the 1990s as one of the most energy-efficient thermal technologies available to humans. Not almost as good, not comparable. Measurably, provably better, at the fundamental task of rejecting heat than any conventional air conditioner working against 95-degree outdoor air. It removes heat from your home. It does not fight the summer. It routes around it entirely. The EPA, writing in the same decade, confirmed that ground source systems represent among the most efficient HVAC technologies ever evaluated. The global HVAC industry is worth over $250 billion annually. That industry sells you compressors fighting outdoor air at 95 degrees. The system uses ground that sits at 55 degrees all summer long. That gap is the whole story. They did not forget this existed. That would be an accident. They buried it. That was not an accident. It was a decision. This is the story of ground source cooling. What it does, how it has been done for over 2,000 years, and why the most efficient way to cool a home was never supposed to reach your hands. Welcome back to Science of Survival, where we open the vaults. Hit subscribe and the bell if you are not already in. Around 400 BCE, on the elevated plateau of central Persia, in a landscape where summer air temperatures climbed past 100 degrees and the sun pressed down on packed clay like a weight, engineers of the Achaemenid civilization were already solving a problem that modern HVAC sales teams would prefer you believe was only recently cracked. They called the structure a Yakhchal. The word translates roughly as ice pit. The engineering was not primitive. It was deliberate, documented, and so effective that many of these structures are still standing today, still measurably cooler inside than the surrounding air. The Yakhchal worked on a principle that required no electricity, no refrigerant, and no service contract. Its base was sunk below grade, deep enough that the surrounding soil acted as a thermal buffer. Its walls were built from a mortar called sarouj, a compound of sand, clay, egg whites, goat hair, and ash, known to be nearly impermeable to heat transfer. The structure tapered upward to a wind-catching tower that drew hot air up and out while the subterranean chamber maintained temperatures cool enough to preserve ice harvested in winter. What they observed was unambiguous. Food placed inside the Yakhchal stayed cold when everything outside rotted. Ice transported from mountain streams survived summer intact. The underground was not merely cooler. It was stable. That stability was the technology. Several centuries passed before anyone in northern Europe arrived at the same conclusion through entirely independent means. By the early medieval period, root cellars were a standard feature of farm construction across what is now Germany, France, England, and Scandinavia. These were not decorative. They were survival infrastructure. A family that lost its root cellar in winter lost its food. The principle was identical to what Persian engineers had formalized centuries earlier and what these European farmers discovered through direct observation and hard failure. Dig down far enough and the earth becomes a refrigerator. Grain, root vegetables, preserved meats, all stored in chambers where the ambient temperature held steady between 45 and 55 degrees Fahrenheit, regardless of whether it was July or January above ground. No written theory, no formal institution, just observable results that passed from parent to child across generations, continent to continent, with zero contact between the civilizations that converged on the same answer. And then, on the other side of the world, in the arid regions of what is now Iran and Afghanistan, the Qanat system. These were underground aqueducts, hand-dug tunnels sometimes stretching for miles, originally engineered to move water from highland aquifers to lowland settlements. What their builders also discovered, and what archaeologists have since confirmed, is that the air moving through a Qanat channel arrived at the surface measurably cooler than ambient air. The underground transit through stable temperature earth conditioned it. Persian engineers eventually formalized this into a system called a bad and Qanat, a wind tower paired with an underground channel that routed incoming air through the earth before delivering it into living spaces. The physics was not theoretical. The results were felt in the room. That is not coincidence. That is thermal mass and the second law of thermodynamics operating before anyone had named either. In the early 1990s, engineers and policy analysts at the U.S. Department of Energy began formally documenting what ancient Persian builders had understood by observation. That ground source thermal exchange is categorically more efficient than air source thermal exchange for heating and cooling buildings. Their findings, published through a series of DOE technical reports and updated repeatedly through subsequent decades, confirmed the physical mechanism with precision. Several feet below the surface, typically between 6 and 10 feet depending on latitude and soil composition, ground temperature ceases to track the seasonal cycle above it. In most of the continental United States, that means stable temperatures between 45 and 65 degrees Fahrenheit year-round. The ground becomes a thermal reservoir. Heat moves, as it always does, from regions of higher temperature to regions of lower temperature. A fluid-filled loop buried in that stable earth carries heat away from your living space and deposits it into a medium that is almost always cooler than summer outdoor air. When outdoor air is at 95 degrees and your ground loop is rejecting heat into 55-degree soil, the thermodynamic advantage is not incremental, it is structural. The compressor in a conventional air conditioner is fighting uphill, pushing heat from a cool space into air that is already hot. A ground-coupled system pushes that same heat downhill into a reservoir that is 40 degrees cooler than the air it would otherwise be fighting. The EPA's assessment, released in the same period, was direct. Ground source heat pump technologies represent among the most energy-efficient HVAC systems available, not as a marginal improvement, but as a fundamentally different approach to the same problem. ASHRAE, the American Society of Heating, Refrigerating, and Air Conditioning Engineers, publishes detailed design standards for ground-coupled heat exchangers to this day, because the engineering is real, the performance is documented, and the principle is not in dispute anywhere in the technical literature. This is the kind of knowledge that used to travel through families for generations, passed from person to person because it worked, not because anyone paid to promote it. That chain was broken deliberately. The question is whether it gets rebuilt. So why is this not in the installation manual of every home built in America in the last 50 years? Here is what a $250 billion annual industry looks like. Carrier Train Technologies, Daikin Bosch, Water Furnace, Climate Master. Every one of these companies sells systems, not principles, systems, installed by certified technicians, maintained under service contracts, replaced on a schedule. Permitted, inspected, and warranted in ways that require their continued involvement at every stage. You cannot patent soil temperature. You cannot trademark the second law of thermodynamics. You cannot build a subscription model around the fact that the earth sits at 55 degrees under your yard. You cannot charge recurring service fees for a buried pipe and a circulating pump that a homeowner installed themselves. That is the financial architecture behind the silence. The ground source principle has been in DOE documentation since the 1990s. ASHRAE has published design standards for ground-coupled systems for decades. The physics is not controversial. What is inconvenient, commercially inconvenient, is a homeowner who understands that the same thermal reservoir their $30,000 professionally installed geothermal system uses can be accessed with pipe from a hardware store, a circulation pump, and a weekend with a shovel or a rented trencher. There are also real structural barriers. Building codes require permits for HVAC modifications. Refrigerant handling is federally regulated. Improper installation can cause moisture infiltration, mold growth, or compressor damage, and industry safety standards exist, in part, for legitimate reasons. But legitimate safety concerns and financial motive are not mutually exclusive. One can be real, and the other can be real at the same time. The result is the same. A homeowner who never hears that the ground under their feet is a cooling system that has been working for free since the earth formed. That is not oversight. That is architecture. Deliberate and sustained. Now, here is exactly what to do with a ground source earth-air heat exchanger, the safest and most accessible entry point into this technology, requiring no refrigerant modification, no electrical permit in most jurisdictions, and no specialized HVAC knowledge. This version circulates air, not fluid, through a buried pipe. Hot outdoor air enters the pipe, travels underground, and arrives indoors pre-cooled by the surrounding earth. No compressor, no refrigerant, no moving parts except a fan. Materials you will need: HDPE or Schedule 40 PVC pipe, 6 to 8 inches in diameter, available at hardware stores and irrigation suppliers. Expect to pay $150 to $3 per linear foot. A circulation fan or inline duct fan rated for your pipe diameter, available at hardware stores for $30 to $80 under brands, including Fantech and Tjernland. Condensation drainage fittings. An inline air filter rated for at least MRV 8. Total materials budget for a basic system, $200 to $500, depending on pipe length and your trench digging costs. Step 1. Plan your trench. You need a minimum depth of 6 feet, deeper in colder climates where frost line is lower. Pipe length should be 50 to 150 feet for meaningful pre-cooling effect. Longer is better. The longer the underground run, the more time the air spends in contact with stable temperature earth. Step 2. Dig the trench. You can rent a trencher from most equipment rental yards for $150 to $300 per day, or hire excavation labor. This is the largest cost variable in the system. Step 3. Lay the pipe with a slight downward slope, approximately 1 inch of drop per 10 feet of run, angled toward a condensation drain point. Standing water inside the pipe is the primary failure mode of this system. Slope is not optional. Step 4. Install a condensation drain at the lowest point of the pipe run. This can be a simple T-fitting with a capped drain stub that you open and clear seasonally. Step 5. Cap the outdoor intake end with a screened filtered cap, RV8 or higher, to prevent insects, debris, and biological material from entering the system. Step 6. Connect the indoor terminus to your space through an inline fan. The fan creates the pressure differential that moves air through the buried run. Run it continuously during cooling hours for best performance. Watch for a measurable temperature drop at the indoor outlet, typically 10 to 20 degrees Fahrenheit cooler than outdoor intake air under normal summer conditions. That is the system working. If you install a simple digital thermometer at the intake and outlet, you will see it. If you see no temperature drop after 48 hours of operation, check 3 things. First, confirm your pipe depth is genuinely at 6 feet or greater. Shallow installation loses the thermal advantage entirely. Second, check for airflow restriction. A clogged filter or undersized fan reduces contact time between the air mass and the pipe walls. Third, check your trench length. A run shorter than 50 feet in very hot conditions may not provide enough thermal contact for significant pre-cooling. For maximum safety, avoid installing the system in areas known for elevated radon concentrations. Radon is a naturally occurring soil gas that an earth-air system can inadvertently channel indoors. Check your region's EPA radon zone map before installation, and consider an inline radon mitigation fan if your area is Zone 1 or Zone 2, $200 to $500 in materials versus $10,000 to $40,000 for a professionally installed geothermal system. The physics does not change based on who installed the pipe. Ancient Persian engineers buried this principle in clay and stone 2,400 years ago. The U.S. Department of Energy and the EPA confirmed the mechanism in documented institutional research, and a $250 billion industry built its revenue model on the assumption that you would never connect those 2 facts into a system. You could build yourself. This knowledge did not disappear. Someone made sure it stayed buried. Drop a comment. What else do you think got buried the same way? If this video opened something for you, subscribe now. The next vault opens soon. What is inside is even heavier than this.